Okay, before we jump into the material of the next unit, since we just took a unit test, we're going to go over some things that will help you manipulate the data in ways that you can better understand it. So the first thing is that we're going to be going over conversions between different units, different size units. We're going to be going over scientific notation and what that means and why we even use it. And then we're going to go over surface area to volume ratios because our upcoming lab that we're going to use is about the cell structure, cell shape, cell size, and why the surface area to volume ratio is important to sustain life. So that's basically the agenda. At the end of the recording, I'm going to ask that you go to a second post on the M&M's chi-squared analysis, where we're going to once again practice a chi-square analysis on a pack of M&Ms that I bought. And so the learning objective for this next unit, that's going to stay the same for this whole unit, is that learners will be able to explain how cell size and shape affect the overall rate of nutrient intake and the rate of waste elimination. Now, learners will be able to make claims and predictions about natural phenomena based on scientific theories and models. And this is all relating to how life is sustained, right? Cells can't exceed a certain size, and there's a reason for that. And then we're going to be using data and like actual calculations to explain that. So in your notes, I'm going to ask that you copy down units of measurement for small volumes and distances. And for the first thing that's going to pop up, it's going to be a conversion from liters. So we're going to convert liters to milliliters. So 1 liter is 1,000 milliliters. So the prefix milli means that this is a smaller volume. So if you take 1,000 milliliters and then pour them all into the same container, you'll only get 1 liter. Okay. And then 1 liter is also equal to, this is the other way to write it in shorthand, lowercase ml is the same as milliliter. And then if you write it into scientific notation, you're moving the decimal from behind this last zero up 1, 2, 3 times behind the 1. And you're going to have 1 times 10 to the, how many times did you move it? 3 milliliters. Okay. And technically in science, you'll learn it more in chemistry. cc stands for cubic centimeter, and that's actually the same exact volume measurement as a milliliter. And it's super cool to know just because we use different measurements across the world, but cc and ml are very uniform across science. Okay, so now we're going to convert that same 1 liter. L is for liter, right? This is the same thing. And we're going to convert that into microliters. And so now if you look at micro versus milli, it takes 1 million microliters poured into the same container to add up to 1 single liter. Now a liter is like a water bottle, right? It's like this much liquid. So if you divide this into a million, basically like water droplets at that point, then that's the amount that 1 microliter is. So it takes 1 million microliters to add up to 1 liter. And if you want to change that into the scientific shorthand, micro is actually a Greek symbol here. And it kind of looks like this right here, where you draw like a U, but has a huge tail in the front. And that is 1 million microliters equals 1 liter. Then if you want to change that into scientific notation, you're going to start with the decimal that's hidden back here because you don't need it when it's a full number, right? And you're going to move it 1, 2, 3, 4, 5, 6 times until it's behind the first non-zero digit. And you moved it 6 times. So that means that you're going to have 1 times 10 to the power of 6 in scientific notation for microliters. And again, this is 1 million microliters, just written in scientific notation, and it equals 1 liter when you add them all up together. It goes the same for meter as well, right? Meter is distance. Liter was volume. So meter, like for example, if you run track, like the 100-meter dash is just 100 meters, right? It's a distance. If you want to use a smaller unit and you have millimeters, right? The things on your ruler, the really, really small increments on the side of your ruler, that is 1,000 milliliters within 1 meter. Okay, so we're going to move that into shorthand now, which is the lowercase m, and meters is also a lowercase m. And then we're going to move it into scientific notation, which means we're going to take the decimal back here, move it 1, 2, 3, up behind the first non-zero number, which is 1, and that'd be 3 movements. So 1 times 10 to the 3 millimeters is in 1 meter. Okay, so if you took 1 milliliter, which is about like the thickness of your nail almost, and you added up 1,000 of them, you would still get 1 full meter stick in distance. So if we want to convert that into micrometers, or micrometers, as some people say, remember that micro means 1 million fits inside of one of the original base unit of meter. Okay, so micrometer has 1 million times to fit in 1 meter. And so we're going to convert that into this micrometer shorthand. And then you're going to take that decimal again and move it 1, 2, 3, 4, 5, 6 behind the first non-zero number. And that would be 1 times 10 to the 6th micrometers. So again, 1 million micrometers equals 1 meter. So what would be useful for you to actually have in your notes would be this little table that tells you for each metric prefix, the abbreviation that you're going to use in front of the main base, and then what power of 10 it actually is related to the base, okay? So the metric prefix for milli is a lowercase m, and it's 10 to the negative 3. So it's 1/1000th of the base unit of 1 meter or a liter or any of those bases. Micro, again, is that weird little U with a tail symbol, and that's 1/1,000,000th of a base unit of like a meter or a liter, okay? Nano is even smaller, and we won't encounter it too much just because biology scales, they go to nano, but we won't work with that much. And that is a lowercase n. So if you did a nanometer, that would be an nm, right? And that's 1/1,000,000,000th of the base unit. So nanos are tiny, okay? So this is again dictating how you move the decimal to change your number into scientific notation. Because once you start working in the millions and the billions, writing all those zeros is going to be a waste of time, and it's going to cause you to make mistakes when you accidentally write an extra one or lose one for no reason when you're just copying some numbers over. Okay, so scientific notation, let's go into a little bit more detail. So for scientific notation, the format is always a times 10 to the b. So a is the ones place, right? You're always going to move the decimal right behind the first non-zero number that is present. It's going to be followed by a decimal and any of the other numbers that were behind that original leading non-zero number. And b is the exponent, required how many times you had to move, or times 10, to move that decimal to get it multiplied by 10 or divided by 10 to get that original number, okay? So scientific notation isn't a new number. It's just changing the format of your number, so you're not writing as many zeros as you would have to if you're working on a really big scale or a really small scale, okay? Because the base number is going to stay the same no matter what. What changes is the exponent usually, and it can be really, really big for really big numbers with a lot of zeros behind them, or it can be really, really small for numbers that have a lot of zeros in front of them, but after a decimal. Okay, so examples of scientific notation numbers that are greater or equal to 1 would be 1, for example, is 1 times 10 to the 0, right? 10 to the 0 power is essentially 1. So 1 times 1 is 1, which equals 1. Okay, 10 is close to 1, but you're going to have to change it to scientific notation by moving the decimal that was originally behind the 0 right behind the first non-zero number, which happens to be the 1 in this case, right? So then you have 1.0 because you've moved the decimal. And how many times did you move the decimal? You moved it 1 time, okay? And the reason you know that this 1 is positive is because originally 10 was bigger than 1. So when you change the 10 into a 1 over here, it was bigger, and bigger numbers are positive, okay? 3 would be 3 times 10 to the 0 because, again, it's already behind the first decimal, so we're not moving it, which means that we're moving it 0 places. And again, 10 to the power of 0 is equal to 1. So 1 times 3 is still 3. Here we have 34. So originally the decimal is hidden behind the 4, and we don't use it because it's behind a number that is whole, and there is no decimal number behind it. So it's still here technically, we just don't have to write it out. So we're going to move it 1 time over behind the first non-zero number, and that is 3. So we're going to have 3.4. Now, is 34 bigger than 3.4? Yes. So therefore, this digit up here for the exponent is going to be a positive. And how many times did we move it? We moved it 1 time from behind the 4 to in front of the 4. So then we're going to have a 1, a positive 1. Okay. So originally I had it as you guys solving it, but I'm just going to use them to explain it at this point, okay? So if you have a 100, the decimal starts out behind the 0. You're going to move it behind the first non-zero number, so you're going to move it 2 times, 1, 2, and it's going to end up right behind the 1, okay? That means our number over here is going to be a 1, right, 1.00, and you moved it 2 times, right? Now we have to figure out if it's positive or negative, and here I have it positive because 100 is bigger than 1. Similar idea to the 1000. Now, the decimal is still behind the original last 0, and we want to move it right behind the first non-zero number. So we're going to move it right behind the 1. So we're going to go 1, 2, 3, and it's going to settle right here. And we're going to have 1 times 10 to the, how many times did we move it? 1, 2, 3, 10 to the power of 3. Is this 3 going to be positive or negative? Is 1000 bigger or smaller than 1? It's bigger, so this is going to be positive. Okay. The example here is 345. So originally the decimal is hidden behind the 5, right? Because it's a whole number, it's hidden. You're going to move it behind the first non-zero number, which is the 3. So in order to get it behind the 3, you're going to move it 1, 2 times. So your new number in scientific notation is going to be 3.45 times 10 to the power of, how many times did you move it? 2. Is 345 bigger than 3.45? Yes, so this will be positive. Okay, let's do 3, 4, 5, 6, 3,456. So the decimal starts out behind the 6. You're going to move it 1, 2, 3 times to get it behind the first digit. So you moved it 3 times. That means your exponent is going to be a 3 above the 10. And now we have our 3.456, which is our base number. And then is this exponent going to be positive or negative? Right, you're going to see if this is bigger than this? Is 3,455 bigger than 3.456? Yes, it is bigger. So then the power up here, the exponent is going to be positive. Okay, same thing with the 4 here. Sorry, so with the 34,567, right? The decimal, you're going to move it in front of the 7, 6, 5, 4, right behind the 3. So you've moved it 4 times. So your exponent is a 4, right? After you've moved the decimal, this automatically becomes your new base number. So 3.4567, and you're going to see is 34,567 bigger than 3.4567? Yes. So that means this 4 stays positive up here. Over here, we also have scientific notation for really, really small numbers, because honestly, writing decimals with a lot of zeros in it is one of the most painstaking things to do, okay? So it's the same format. It's a times 10 to the b, where b is a negative exponent to show how many times that ones place digit must be moved or divided by 10 to get the same number. So here, we're not multiplying by 10 anymore. We're dividing by 10, okay? Because these are numbers that are smaller than 1, okay? So here's a visualization of what actually happens. So if you have a 10 to the power of negative 1, right, a negative exponent up here, it means that technically you're actually dividing by 10 to the power of 1, right? The negative acts the same thing as acting as a denominator instead of a numerator. So instead of multiplying like you did on the previous page here for big numbers, when you have small numbers, you're actually going to be dividing because this ends up in the denominator, right? So 1 over 100, if you're dividing something by 100, you're actually dividing by 10 to the power of 2, or 10 squared. And if you want to move that up into the numerator, then you would just turn the exponent into a negative. Okay. So here, as an example, we have 0.10. And this is a number that is smaller than 1. And we want to write it into scientific notation in a way that kind of looks easier and is easier to manage. So we want to move the decimal behind the first non-zero number, and that happens to be 1, which means we're going to move it to the right 1 time. Okay, that changes our number from 0.1, and then when we move the decimal behind the 1, it becomes 1.0. How many times did you move it? You only did 1 hop, so the exponent is 1. Is 0.1 bigger or smaller than 1? It's smaller, therefore this exponent is negative, okay? 0.23 is the same idea, okay? We're only ever going to move the decimal behind the first non-zero number, right? The first non-zero number is 2, so we're going to move the decimal behind 2. We're never going to move it behind the 3, because then we'd have 23 over here, and we always have the decimal after the first non-zero number. So if we move it 1 time, that means our exponent is going to be at 1. Now we want to know if the exponent is positive or negative, and we want to see, is 0.23 bigger or smaller than 2.3? It's smaller, right? It's actually 10 times smaller. So since this is smaller than this, we're going to have a negative exponent up here, right? So over here, for example, we are moving this 2 times. So our exponent is going to be a 2, and it is negative because 0.01 is a lot smaller than 1. Okay, 0.001, you're going to move 1, 2, 3 to get it behind the 1, and then 1.0 times 10 to the negative 3, and it's negative again because 0.001 is smaller than 1. Okay, 0.0001, same idea, you're going to move it 1, 2, 3, 4 to get it behind the 1, and it's going to change into a 1.00, right, because there's 2 zeros behind here, times 10 to the negative 4. Now it's negative because 0.000100 is smaller than 1.00. Okay, from just listening to me say all these zeros, you already realize how complex it is to just remember and then not make a mistake of how many zeros there are in a number. So if you're working with numbers that have a lot of zeros in them and you're prone to making mistakes, scientific notation is an easy fix because after you change into scientific notation, you already dropped 1, 2, 3, 4 zeros that you have to worry about, right? You're only worrying about the ones after the non-zero number because those are significant. Okay, so again, if you have 0.0234, you're going to move it behind the first non-zero number, so you're going to move it behind the 2. That means you have 2.34, and you have to hop 1, 2 times to get there. And 0.0234 is smaller than 2.34, so you have a negative 2 up in the exponent. Okay, 0.002345, doesn't matter how the n changes, it only matters where the first non-zero number is. So you're going to move it 1, 2, 3 times. And it's going to be a negative 3 because this number is a lot smaller than our new base number. Once you move the decimal behind the 2, you get 2.345 times 10 to the negative 3. Same down here, you're going to move it 1, 2, 3, 4 to get it behind the 2. So 2.345 times 10 to the negative 4. As you can see, the only difference between these two numbers is that extra 0 after the decimal and before the non-zero numbers here. And therefore, these bases are the same, but their exponents are different. And I want you to keep in mind that 0.000235 is still the exact same number as 2.345 times 10 to the negative 4. It's just in a different format. That's it. Okay, so you have some practice problems here to think about. Okay, so again, the scientific form you're aiming for is a times 10 to the b. So if the decimal is behind the 0 right now, and you want to move it behind the first non-zero number, it means that you have to move it behind the 1. So in order to move it behind the 1, you have to jump 1, 2 times to get in front of the 5 and behind the 1. That means your new base number is going to be 1.50, and you jump 2 times, so it's a 2 up here. Now this 2 is positive because 150 is bigger than 1.50. Okay, let's go from the other end now, 0.0015. This number is smaller than 0, which means you already know that your exponent is going to be negative. Right? You're going to take this decimal and move it behind the first non-zero number, which is going to be the 1. So you're going to do 1, 2, and 3 to get it behind the 1. So that means that your exponent is going to be a 3, and you know it's going to be a negative 3 because this number is smaller than 1.5. So 1.5 times 10 to the negative 3 is the same number as 0.0015. It just is in an easier format to work with because now this has whole numbers on it. Okay. Here you'd be jumping 1, 2, 3, 4, 5 to get behind that 1. So you're going to have 1.5 times 10 to the negative 5. 5,000 is bigger than 1, so you know your exponent is going to be positive, and you're going to move it 1, 2, 3 to get behind that 5, and you're going to have 5 times 10 to the positive 3. Lastly, you have 0.5, and now we could say this is super close to having a non-zero number behind in front of the decimal, but it's not quite. So we're going to want to move that decimal behind the 5, and so we're moving it 1 time. And we also know that 0.5 is smaller than 5. So when we have 5 times 10 to the negative 1, it's a negative because 0.5 is smaller than 5, and that's pretty straightforward. So when we have volume conversions, we talked about micro, we talked about milli, we talked about nano. You should be able to convert, and when you convert them, they actually are easiestly converted in scientific notation, okay? So when you have 1 milliliter, you have 1/1000th, right? So if you're dividing by 1,000, instead of having the 1,000 at the bottom, you can just move it to the top and multiply, but change the exponent to a negative, because technically you're dividing it still. Just a different form for the same information, right? Instead of writing all these zeros for micro, 1 millionth, you can just instead 1 times 10 to the negative 6, right? Because there are 6 zeros that you're hopping on. Nano would be billion, which would be negative 9, right? Because you're originally dividing it, which means that this number is really, really small. And pico is even smaller. It's 1 trillionth, okay? Negative 12 up here. So if you're converting 1 milliliter to 1 microliter, remember, milliliter is bigger than microliter, right? 1 milliliter is 1,000 microliters. So you're going to write 1,000 microliters. Now it's the same thing as writing 1 times 10 to the power of 3 microliters. Right, 1.5 milliliters is equivalent to 1,500 microliters. You can see that since the 5 was already behind the decimal, when you move the decimal 1, 2, 3 times, only 2 more zeros get added in. But if you compare the spacing, they still have the same number of digits between 1 and 1.5, okay? 0.5 milliliters, if you move the decimal point 1, 2, 3, you're gonna add 2 zeros behind the 5, but there's no 1 in front, so you just get 500 microliters. And 1.25, as you move 1, 2, 3, you would get 125 microliters. And that's how you would convert milliliters to microliters, just because you know it takes 1 liter to get to 1,000 milliliters. It takes 1 milliliter to get to 1,000 microliters. Okay, because when you go from 1 liter to 1 microliter, you're going to get 1,000 times 1,000, which is 1 million, right? Because 1 million microliters fits in 1 liter. So you're jumping 3 at a time if you stop in these increments. Okay, so if you're converting to microliters, 0.5 milliliters, right? You're going to move 1, 2, 3, and you're going to fill in 2 of those spaces with zeros. So 0.5 milliliters becomes 500 microliters. 0.45 milliliters becomes 1, 2, 3, becomes 45 milliliters, 45 microliters. And then 0.001 milliliters, if you move it 1, 2, 3 times to get to microliters, you're going to get exactly 1 microliter, right? So if you divide a milliliter by 1,000, that's when you get 1 single microliter, and that's how small that is. So this is just some information for you to know. You don't have to write this down, but cells range from the sizes of 1 millimeter down to 1 micrometer in diameter. So some of them are really, really small, like micrometers, and some of them are actually visible to the eye in milliliters, okay? Cells need a large surface area of membrane to adequately exchange materials. They need to get rid of waste by pushing it out of their membrane, and then they need to intake nutrients and absorb materials, so they need to bring them in. So if you don't have enough surface area and you have too much volume, that means you're not going to be able to get stuff in and out of the cell efficiently, and then cell processes slow down, and the cell could eventually die from that, okay? Here are the things on the scale from 0.1 nanometers, right, 1 billionth of a meter, all the way up to 1 kilometer, which is 1,000 meters, okay? It kind of gives you a reference of that. Each increment of size, what's a good representation of that? So I'm going to ask that in your practice, you're also going to do something similar as a follow-up to this section. So you're going to draw cubes and then calculate the surface area and volume for each in order to find the surface area to volume ratio. So I'm going to do the 1 centimeter cube with y'all, and then on your worksheet, you'll do the 2 centimeter and the 3 centimeters, okay? So how you find surface area, you're going to need to find the base, the width, and the height measurements separately, okay? So for the 1 centimeter cube, it's a cube, right? So all sides are the exact same. So your base, your width, and your height are all going to be 1 centimeter. Now, the way you find surface area of a cube or any rectangular prism is going to be 2 times the base times the width, right? So if you get the base times the width, you're going to get this face. But you need 2 because there's 1 on this side and there's also 1 on the opposite side that's facing away from you right now. And then you're going to want to find 2 times width times height. So you want width times height in order to find this side. And it's 2 because there's 1 over here and then there's also 1 on this side facing away from you. Okay. Lastly, you're going to want to find base times height over here, and that's going to be on the bottom and the top surface. That's why it's times 2. And then once you find all of these and you add them up, that is going to be your surface area number, okay? So in this case, we would be multiplying 2 times 1 centimeter times 1 centimeter because as you see, B and W are both each 1 centimeter. 2 times W times H is 2 times 1 centimeter times 1 centimeter because W and H, width and height, are both also 1 centimeter. And then base times height is 1 centimeter times 1 centimeter. And again, there's 2 because there are 2 faces of it, okay? Then you're going to take all 3 of these numbers that you have calculated out, which is 2 centimeters squared. Remember, the units also get squared when you multiply them. And you're going to add them all up together to get 6 centimeters squared. Okay, that is your surface area. We're not done yet because this is our end goal. Now you're going to find volume. Okay, volume is always the formula base times width times height for a cube. Pretty simple, right? So your base times width times height. Base is still 1 centimeter, width is 1 centimeter, height is 1 centimeter. So when you plug and chug, you're going to get 1 centimeter times 1 centimeter times 1 centimeter, and that's going to end up with 1 centimeter cubed again, because the units still multiply. Now, our end goal is to find surface area to volume ratio, because that's what we take into consideration when we talk about cell sizes. The surface area to volume ratio is going to be basically you're taking the surface area as a numerator and volume as a denominator, and you're going to divide the top by the bottom. Therefore, you're going to plug in your numbers, which is the surface area of 6 centimeters squared and your volume of 1 centimeter cubed, and you're going to get a ratio in the end of 6. Okay. So when we compare different cells, when we compare different shapes of cells, we're going to be comparing their surface area to volume ratio, because the bigger this ratio, the better cells are at absorbing and exchanging materials. The smaller this ratio, the more difficulty they have, and the more likely the cell is going to stop growing and instead split or die. Okay, so you're going to go ahead and calculate for 2 centimeters and 3 centimeters on your own as your practice. The last part now is to do the surface area and volume for the following solids. So you have one rectangular prism here. Remember, you're going to want to list out your base and your height and your width, so that when you do your calculations and you're plugging in the numbers, you don't get confused with them. Okay, remember that the formulas for surface area is 2 times base times height plus 2 times base times width plus 2 times width times height. And then volume is base times height times width, okay? And in the end, when you're finding your ratio, you're going to take the surface area number you calculated and divide it by the volume, and that's just going to be your ratio, okay? You want to see that ratio in comparison to the same exact volume of cube, right? So the volume is going to be the exact same, but the surface area now is different because the same cube has been cut into 27 mini cubes, okay? That means that every single cube of yours has 6 faces that are exposed to the environment where they can exchange materials. But when you add them all up together, the volume is still the exact darn same. Okay, so I'm going to ask that you calculate your surface area for this cut up cube, right? I'm going to give you a hint. It's going to be a much larger number than the surface area you found here, because now each little cube has 6 sides that you have to consider, right? Each side is divided by 3. So one of these is going to be 1 millimeter in height, and then it's going to be 3.1 millimeters in width, and then it's going to be 4.2 millimeters in, what is it? In base, I guess. Sorry, I forgot. I lost track of which third measurement I was on. But so you're going to find the surface area for each one of them, and then you're going to multiply them by however many cubes there are to find the actual surface area. So that's going to be a lot more than before. But the volume is the same, okay? And the comparison I want you to think about is on cell surfaces. So up here you can see a typical, for example, like a muscular or an epithelial skin cell, which is smooth surfaced, right? So cells like this, they don't have a huge ratio because they're smooth surfaced. But over here, this kind of cut up cube more resembles things like this, where it's like the inside of your intestine, where you have villi, which are folds in the cells that allow for more surface area. Therefore, in your intestines, you get more absorption, whether it's of nutrients and water. So it just increases the efficiency of any process that's going through the intestine, okay? So your practice worksheet is closely paired with this. As you work through this, you can stop and pause each section and go and work on it, or you can work along or after, okay? After this, you're going to complete this and turn the form in to me. You can either do it on your own or you can do it on the Word document, although I find that a little bit difficult to do. And then you're going to move on to your M&M chi-squared lab, which you're going to complete by next class period that we meet, which will be on the 13th, which is a Tuesday. So that's in a while. Don't wait till the last minute to do it though, okay? If you haven't yet done your test, it is going to be due at midnight before the weekend starts. So make sure you get on to that. And then if you haven't done your progress check, that would have been more important to do before the test than later, because it was the review for your test.